Hi students, I am Dr. Ravi Kumar, Associate Professor, Department of ECE, Institute of Aeronautical Engineering. So, this class I am going to discuss some definitions and terminologies which are used in analog and digital electronics. So, let us see that there are some definitions and terminologies which are in Module 1. So, we know that in analog and digital electronics, the Module 1 deals with the semiconductor materials and construction of p-n junction diode, and then the application of p-n junction diode. Let us see some of the definitions and terminologies which are helpful to understand the students the concept of semiconductors which are there in module 1. So first we'll see that define semiconductors. If every student might have known that the semiconductor definition, so that it is the basic introduction to this first module. So basically, materials are broadly classified as metals, conductors, or like insulators and semiconductors. When we see this, the conductors have rich conductivity, insulators have poor conductivity, whereas in semiconductors have electrical properties lies between conductor and insulator. So I think this insulator and conductors and semiconductors, the distinguish between them has been explained by this energy band diagram. It is beautifully defined, the difference between these three, by the energy band diagram. Let us see that energy band diagram. So by which we can easily understood that the characteristic between these conductors, insulator and semiconductors. So if you see this figure, the energy band diagram for all these three materials. So the left side is insulator and the middle is semiconductor and the last one is right side is conductors. If you see this energy band diagram, when I am talking about energy band diagram, it is a group of energy levels of a particular material or particular of an atom. So the group of energy levels are basically can be grouped into valency band or group and conduction band or group. So initially all charge carriers of energy levels are present in the valency band. So before applying any external force or temperature to the particular material, then all charge carriers are presented in a valency band. Valency band means it is one type of energy band. For example, E1, E2, E3, E4, having different energies of a particular material. So they are all grouped into a band which is called valency band. So this valency band, initially all charge carriers are presented in the valency band. What happens when it is like an application of some external force or some external voltage we can given to the material? Then the charge carriers are presented, which are presented in the material, have excited and move from one energy level to other energy level. That energy level is called other energy level is called, we can call it as a conduction energy level or conduction band. So whenever take these materials into some temperature, then the charge carriers which are there in that material gets excited, gets energized and move from one energy level to another energy level. So in this case, in a insulating material, for example, insulating material, mica, wood and plastic, if you take any material and the bonds which are, the atoms which are bonded with that kind of material, if it is taken to some external temperature or some force given to that, then the electrons which are there in the valency band get excited and move from valency band to conduction band. But in the insulating material, the energy gap is almost greater than 5 electron volts. 5 electron volts. So the energy gap measured in electron volts. So this gap is greater than 5 electron volts. due to which the charge carriers or electrons does not have energy to get from valency band to conduction band, so that they are not reached to the conduction band, so that in result the conduction in insulating material is zero, or no current flow in the insulating material. So this is what we observe. Whereas in conductor, when it comes to conductor, so initially the all charge carriers are presented in the valency band, but a small voltage, a little voltage is given to the conductor. Immediately the charge carriers are get energized and move from valency band to conduction band. So it requires no energy. It is almost zero energy. Just above the zero energy, the charge carriers are gets energized and move from valency band to conduction band. To represent that one, we have given that coincident or like overlap of the bands. So it is almost the conduction band also very near to the valency band, or otherwise it is overlap with the valency band, so that the moment when we are giving to the energy to the conductor, or the moment when we are providing some voltage to the conductor, immediately without any delay it reaches to the conduction band, so that we can have a zero energy gap. That is represented by this last right side figure. What happened in the middle one, the most important, then that is what we have taken the definition of semiconductor. So even the energy gap is lies between insulator and the conductor. And the electrical properties also lies between insulator and conductor. So if you take the example of semiconductor, silicon and germanium and gallium arsenide, so these are, if you take that, or initially the charge carriers or electrons are presented in the valency band. The moment when we are giving some voltage like 0.67 for germanium or 1.1 electron volts for silicon intrinsic semiconductors, then the charge carriers are get energized and move from valency band to conduction band. This gap is medium between conductor and the insulator, so that we can have some controlling current flow in the semiconductor material. So finally, the defined semiconductor means the materials which follows or which having a electrical characteristics of lies between conductor and insulator. So that is called semiconductors. The name itself says that semiconductors, and also the examples of semiconductors are germanium and silicon. And the valence electrons which are there in the semiconductor materials are like 4 valence electrons. We have all seen in our theory classes. You might if you want to know, then go to that particular slides. Then the most important thing is doping. So what does it mean, like doping? So basically in theory classes, I explained and I told you that if you have a semiconductor silicon and germanium, the atomic structure for silicon is the basic structure I'm going to draw here. It is a basic structure for silicon and germanium. If you take this one, the circle is represented by atom, silicon. You know that silicon and germanium having 4 valence electrons. So this silicon atom having 4 valence electrons are covalent bond with the neighboring silicon atom. This is covalent bond with the neighboring silicon atom. This is covalent bond with the neighboring silicon atom. So similarly, if you replace that circle with the germanium letter, then it will become as a germanium atom. So it is an intrinsic semiconductor. So in theory, we have seen that in the best analogy of pure and impure water, the current flow in the pure and impure water, the current flow in the salt water is always greater than the current flow in the pure water. Okay. Similarly, the current flow in the intrinsic semiconductor is the current flow in the extrinsic semiconductor is more than the intrinsic semiconductor, because in this intrinsic semiconductor, it follows that as we increase the temperature, the conductivity decreases at some time. after some time. So in order to improve the conductivity, we shifted that intrinsic semiconductor into extrinsic semiconductor. So in order to improve the conductivity. So how to do that one? By the process of doping. So now we will see that what is doping. Doping is a process of adding impurities to pure semiconductor. Pure semiconductors are called germanium and silicon. Intrinsic semiconductor also called pure semiconductor. Examples are germanium and silicon. If you see it, if you repeat this structure into left side right in a two-dimensional form or three-dimensional form, you will get this like a silicon atom, silicon structure. So this how can we adding these impurities to the pure semiconductor? For example, when we replace this one, like indirectly, we are taking this semiconductor into some temperature and then it will become as some liquid. Then take the impurity liquids and inject it into that pure semiconductor liquid. Then it will become like a covalent bond with this impurity atoms to the pure semiconductor. So the simple example which is shown in figure is, for example, if I am injecting the some trivalent atoms. Basically, we have a 4 valence electrons of semiconductors and a trivalent atoms and 5 pentavalent atoms of adding to with this 4 valence electrons of semiconductor, it will become as extrinsic semiconductor. If we add trivalent atoms, the examples of trivalent atoms are the examples of trivalent atoms are the examples of trivalent atoms are boron, aluminum, gallium, indium. The examples of pentavalent atoms are phosphorus, arsenic, antimony, bismuth. These are the examples of pentavalent atoms. When we combine this pentavalent atom with this semiconductor material, we will get this N-type, and if we combine with the trivalent atoms, we will get the P-type material. Let us take an example of boron. If you add this boron atom, you know that boron, aluminum, gallium, indium having 3 valence electrons. These 3 valence electrons are covalent bond with this neighboring silicon atom, and one place is vacant with that vacant space created, that is called hole. So in this way, the process of adding impurities to the pure semiconductor is called doping. In semiconductor materials that has been subject to the doping process is called extrinsic material. There are 2 types of extrinsic material, P-type and N-type. If we add impurities of trivalent atoms to the semiconductor material, you will get P-type material. If you add pentavalent atoms like phosphorus, antimony, arsenic, bismuth added with this semiconductor material, you will get N-type material. So if you add phosphorus, then phosphorus having 5 valence electrons, 4 valence electrons are covalent bond with the neighboring atoms, and 5th valence electrons are loosely bond with the parent atom, phosphorus atom. Then this excess electron, this is excess electron or free electron. So once we talk about this doping, when after adding trivalent atom to the silicon or germanium pure semiconductor, it will become as a P-type, and after adding pentavalent atoms to the pure semiconductor, it will become N-type. Then you have a ready with that p-type material and n-type material. So everyone know that. So how can we make that p-n junction diode is take the p-type material and take that n-type material and joining together, you will become like it will become as a p-n junction diode. So this is like it is just simple adding of p-type and n-type together to get the p-n junction diode. Concentration gradient. This is most important definition of terminology. The gradient nothing but changes occur, and the concentration gradient nothing but concentration gradient is nothing but it is occurs when the concentration of charge carriers are higher in one region than the other region. If you see this figure, it has these are the charge carriers. So there are basically eight charge carriers. Here only 4 charge carriers. So this region, the left side region having 8 charge carriers, right side having 4 charge carriers. The graph, if you move from left side to right side, so the higher concentration to lower concentration. So is there any reason inside, in particular to the semiconductor material, any reason having one side is more concentration of charge carriers compared with the other reason, then there would there would exist a concentration gradient. So due to which charge carriers have a tendency to move from higher concentration to lower concentration. So if you take a p-n junction diode, in the p type having majority charge carriers of electron holes, and in the n type majority charge carriers are electrons and minor charge carrier holes. Here minor charge carriers are electrons. So here 9 holes and 2 holes. This kind of difference in the charge carriers are called concentration gradient. Here on the n side 9 holes, on p side 2 holes only. On the n side 9 electrons, on p side 2 electrons only. This kind of situation, this kind of presence of charge carriers inside any material, then there should be exist a concentration gradient. Due to which charge carriers having tendency to move from one place to higher to lower, so that junction will be formed in the p-n junction diode. That is the story about all those things we have seen in the videos. Next, cut-in voltage. It is most important definition. Cut-in voltage in p-n junction diode. If you see this graph, p-n junction diode, VI characteristic. Initially, both P and N are electrically neutral. After applying the forward bias voltage, so for lower values of voltage are up to cut-in voltage, current the current possessed by the p-n junction diode is 0. So the 0 current flow due to the applying voltage is less than cut-in voltage. Once reached to the cut-in voltage or certain voltage, which is minimum voltage to establish the current flow in the p-n junction diode, so then the current will start in p-n junction diode. That point is called cut-in voltage. The point where the current flow start to flow current in a p-n junction diode is called cut-in voltage, V gamma. Next, dynamic resistance. Dynamic resistance, once the nonlinear behavior of this curve, and once you get the curve measured by voltage and current, definitely it is not linear, it is not a straight line or zero slope. Then definitely there will be slope, means it possesses some resistance, because a p-n junction diode applied voltage is given and the current flow in the p-n junction diode, means definitely it possesses some resistance. And also from the graph we can measure the dynamic resistance it is a slope, take the tangent line, take one point and take the tangent line, the slope in y-axis to the slope in x-axis, the ratio of slope in x-axis by slope in y-axis are simply 1 by slope, 1 by slope. The change in x-axis by change in y-axis, Otherwise, dynamic resistance is nothing but 1 by slope. Slope is nothing but dy by dx. Dy by dx nothing but di by dv. Reciprocal of slope nothing but dv by di. So r is equal to v by I, dv by dvd by did. So we can get the dynamic resistance simply calculating this reverse slope of the given curve, diode curve, characteristic curve. So we will get the dynamic resistance. It is the most important factor. So by which we can take the whether that less resistance possessed by the p-junction diode in forward bias and high resistance possessed by the p-junction diode in reverse bias. And diffusion capacitance and transition capacitance, simply same capacitor, like p-junction diode act as a parallel plate capacitor. So negative charge accumulated on p side and positive charge accumulated on n side. So this is like a plate and this is like a plate. This is like a dielectric medium, so that it will act as a capacitor, parallel plate capacitor. And based on the forward bias and reverse bias, by the connection of biasing, it has diode has diffusion capacitance in forward bias and transition capacitance in reverse bias. And finally, we will see that rectifier. Rectifier is the important application of an p-junction diode. Define what is rectifier. Rectifier is an electronic circuit which converts AC input signal into pulsating DC signal. If we are giving any AC signal which converts a rectifier converts a pulsating DC. This is called pulsating DC. This pulsating DC can be further purified or can be further processed. You will get the perfect DC, like pure DC. This is zero. The pure DC having no fluctuations. So in order to achieve this one, the first step is that first we have gone through that AC signal into through the rectifier, then you will get the pulsating DC. So in order to measure those signals of that AC components are present, DC component present in the rectified output, you have take mathematical equation of V average, VRMS. Then you will take that ripple factor. It is a definition VRRMS by VDC. The ratio of VRRMS by VDC can be measured by ripple factor, through which we can measure that how much component DC component present in the rectified output. And then you will achieve some factors. You will get some factors based on that value, whether it is like an half wave rectifier having 40% ripple, 80% ripple. As we go to the full wave and bridge rectifier, that ripple factor gets reduced. So that ripple value gets reduced means how much AC component present in the rectifier output. And efficiency is the ratio of DC output power to the AC input power. How much AC is given, then how much DC will get from that rectifier. So PDC by PAC, you will get 40, 0.406 efficiency in half wave rectifier, 80% efficiency in the full wave rectifier. These are the some important definitions in the part, like module 1. And if we see the filter, like use the inductor filter, capacitor and inductor capacitor combination filters used to get further reduction of the AC component present in the rectifier output. These are the references helpful to get that definitions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.